Oh, some running before the class. Okay, just some movements to keep me active and then to help me move around so that I can flexibly teach you, because flexibility is important. All right, so that's it. Okay, I've done enough before I came here. It's just I'm doing this so that I can tell you that I have done it. Okay, so hello my dear students, I hope you're all doing well. My name is Benatang Paton and I welcome you all to the channel Classroom, where we learn together. So today my dear students, we are going to discuss a very important topic, which is force on a current carrying conductor placed in a magnetic field. Now, to save time, I have already drawn the diagram here. But then, no, I will not tell you. Okay, I will not start with this right now. Before we go into this, we will do a short revision. Okay, so that we prepare ourselves with the concept, which will help you understand this. Okay, I promise you, after the revision, this will be easy peasy for you. Okay, it will be very easy, so you'll just understand easily. So let's go and do the brief revision, and let's come to this core topic, which will be a piece of cake much later. Now, if there are any new students joining in, I warmly welcome you all, to learn together. And then the rule here is, every time we learn, we take out our notebook, grab a pen or a pencil, and then we write down, because whatever we discuss here is going to serve as a very good notes for you. So I will recommend you all, to write down the notes, so that it will help you get a good understanding on the topics. Okay, so without wasting any time, let's jump into the topic and let's learn. Now, there's a statement for this particular topic. So let's first write down the statement and then we'll proceed with the discussion. So let's write down the statement. So the statement reads, let's write down the statement together. The statement goes like, when a current carrying conductor is placed inside an external magnetic field, then the current carrying conductor experiences a magnetic force. The current carrying conductor experiences a force which is mutually perpendicular to both current and magnetic field. So that is the statement. Let's write down here. So the statement reads, when a current carrying conductor is placed inside an external magnetic field, the current carrying wire or conductor, you can write any one, let me use wire, conductor. The current carrying conductor experiences a force which is mutually perpendicular, which is mutually perpendicular to both magnetic field and the current. So my dear students, kindly write down this statement, because this statement is very important. So this is a very short statement, but then a very important statement, which reads, when a current carrying conductor is placed inside an external magnetic field, the current carrying conductor experiences a force which is mutually perpendicular to both magnetic field and the current. Okay, so now I will erase this, assuming that you have written this. You can pause the video and then you can write it. Okay, So assuming that you have written this, let me erase this, and then let us go deeper into our topic, which is a short revision on the topic before we jump and we start in detail about this. So the revision will be done from Oyster's experiment. We are all familiar with Oyster experiment. A video on Oyster experiment has been uploaded. I think it is the second or the third video. So it is there in the channel. So let us have a quick review from there, because it all started from there. Okay, so let's review. Let's do a brief revision and understand this topic better. So in Oyster experiment, which was performed by Hans Christian Oyster, he took a wire, and then a magnetic needle was kept nearby along the wire. Okay, so there was a magnetic needle which was kept near the wire. Now, this is the needle. This is the needle. Remember, my dear students, that the needle is a magnetic needle. Okay, this is a magnetic needle. So it has got its own magnetic field lines. Remember this. Now, when current was made to pass through, so negative terminal, short, long is positive, short, long, because this is a battery. Okay, so when current was made to pass through, this is the positive terminal, this is the negative terminal. So current will flow from this end. So current is flowing here, and it will enter the negative terminal. When current was made to pass through this wire, now what did he observe? He observed a deflection in the needle. So he observed a deflection in the needle. So the needle deflected. This is what he observed. Okay. So what made the needle deflect? Or why did the needle deflect? Now we know the answer. The answer is because the needle experienced a force from the current carrying wire. The current carrying wire exerted a force on the magnetic needle. So a force was exerted by whom? By this current carrying wire on the magnetic needle, because of which this needle deflected. Okay, so a force was exerted by the current carrying wire on the magnetic needle, because of which the magnetic needle deflected. So this is what actually happened. Now, what type of force? Since it was a force, let us try to identify what type of force are we talking about. So what do you think? What type of force exerted? What type of force was exerted on the magnetic needle? A magnetic force was exerted. Remember this, very important. The type of force which was exerted by the current carrying conductor on the needle was a magnetic force. Now, what is the origin? So, what is the origin of this force? How did this wire produce magnetic field? How did this wire produce magnetic force? It's just a wire, isn't it? It's just a wire. So how did this wire produce magnetic force? Isn't it? It's interesting now how a piece of wire is able to produce magnetic force. We want to know. Okay, so what is the origin? So I want to know, like, how did this piece of wire produce magnetic field? Okay, then we know the answer. Which is a piece of wire by itself will not produce magnetic field, because this was again demonstrated by Oyster himself. Because at the very beginning of the experiment, when no current was passing through the wire, he did not observe anything in the needle. That means the magnetic needle behaved normally. So there was no deflection in the needle when there was no current in the wire. This is the wire. Okay, this is the wire where no current is flowing in the wire at this moment. So when no current was passing through the wire, the needle did not deflected. But immediately when current started to pass through the wire, the needle underwent deflection. The needle, which was like this, deflected. Okay, the needle which was like this, so the needle which was like this started deflecting. Okay, and it remained in this position. Okay, as long as the current was passing. And when we switch off, when current flow was switched off, it went back like this. Again, when the path of current was restored, again it went like this. So as long as the current was flowing, the magnetic needle would remain in its position, plus the magnetic needle showed deflection only when current was passing through the wire. But when no current is passing through the wire, the needle did not show any deflection. Why? I want to know why. Why? Why is the needle not showing any deflection in this scenario? That's because there is no current flowing here. That means there is no current flowing here means no magnetic field. So this wire is not producing any magnetic field. But, my dear students, this current carrying wire, this wire which is carrying a current, this wire which has now become a conductor, a current carrying conductor, which is now a current carrying conductor, okay, now produces magnetic field. A current carrying wire produces magnetic field, okay. And what is the nature of the magnetic field produced by a current carrying wire? It is circular, concentric circles, is it not? Okay, it produces magnetic field, okay, in the form of concentric circles. A straight current carrying wire produces concentric, okay, magnetic field in the form of concentric circles. So this current carrying wire is producing magnetic field in the form of concentric circles. So now this wire, this current carrying wire, is producing magnetic field. This magnetic needle itself has got its own magnetic field. So two magnetic field lines are interacting. So this has got its own magnetic field. From north to south, the magnetic field lines will emerge, and then we have this current carrying wire producing magnetic field. So these two magnetic fields will interact. My dear students, when two magnetic field lines interact, there can be two possible interactions, okay? There can be two possible outcomes. It can be a force of attraction, or it can be a force of repulsion. I repeat, when two magnetic forces interact, when two magnetic field lines interact, there can be only two possible outcomes. There can be only two possible relationships. What are those? It can be, okay, so let me just write on here. So when two magnetic field interact, when two magnetic field interact, there can be only two outcomes. What are they? It can be a force of attraction. The interaction can be that of attraction, or the interaction can be that of repulsion. Now, when will it be attraction? When will it be attraction? Can anybody tell me, my dear students? Who will tell me when will it be attraction? We are all familiar with magnets, isn't it? We are all familiar with magnets. Every magnet has got two poles, north and south. So this is A, this is B. So when will it be attraction? So the magnets at position A, will they show attraction, or the magnets at position B, will they show attraction? When will they show attraction? Oh, sorry, my poles are all similar, they are same. Sorry, let's make it like this. Okay. So when will it be attraction? When will it be attraction? Now, who will tell me when it will be attraction? Yes, you're correct. B, okay, magnetic field at B, this B, okay, position B will give me attraction. Why? Because we know that opposite poles attract, okay, and then repulsion will be A, because like poles is not here, south and south pole, okay, repulsion, this is south and north pole, they will attract each other. So remember, when two magnetic field lines interact, there can be only two possible outcomes, okay, it can be a force of attraction, or it can be a force of repulsion, okay. I hope that's clear. So that's what is happening here, okay. So the magnetic needle is deflecting because a force is generated. See, attraction is a force, my dear students, and attraction is also a force. In the same way, repulsion is also a force. This is force. These are two types of forces only. Attraction is a pull force, repulsion is a push force. Are you getting my point? Okay, so when two magnetic field lines interact, there will be a force, and because of this force, this magnetic needle, okay, deflected. In the absence of this force, it does not deflect. No force to none, no force. And why no force? Because no current, because this is just a plain wire, just a normal wire, okay, nothing is happening, even current is not flowing. So this wire is not producing any magnetic field. So this is the only object which is magnetic, so it is not under the influence of any external magnetic field. So why will it deflect? Why will it deflect? It won't deflect. But when current will flow, okay, but when current flows through the wire, what will happen? The current carrying conductor will start producing its own magnetic field. This magnetic needle has got its own magnetic field. So two magnetic forces will interact, and a force is generated. Because of the force, the magnetic needle undergoes deflection. So I hope, my dear students, that it is clear enough. Okay, so now let's continue with the discussion further. Now I want to ask a question. Now in this experiment, it is the needle which is undergoing deflection. Okay, it is the needle which is undergoing deflection. Okay, now why not? Okay, it is the needle which is undergoing deflection and not the conductor. In this experiment, it is the needle which is undergoing deflection and the conductor is not undergoing deflection. But Newton's third law of motion, Newton's third law of motion, Newton's third law of motion, the Newton's third law of motion states that, what does it state? It states that for every action there is an equal and opposite reaction. Okay, let me not read it, but just remember that now we're discussing about Newton's third law of motion. So Newton's third law of motion says that for every action there's an equal and opposite reaction. That means, so the conductor is exerting a force on the needle, because of which the needle undergoes deflection. Following Newton's third law of motion, okay, following Newton's third law of motion, we come to know that even this magnetic needle is exerting a force, an equal and opposite force on the current carrying conductor. But the current carrying conductor is not undergoing deflection. The current carrying conductor remains in its original position, whereas the needle is the one who undergoes deflection. Okay, why? Because here the magnetic needle is free to move. Okay, the magnetic needle is free to move, whereas in this experiment the conductors are fixed. Okay, they are fixed. The conductors are fixed. So even in the original experiment, which was done by Oersted in front of his students in his classroom, as what I know, okay, and as per the description of the experiment, this conductor was placed on the table. So there was a support for the conductor. Okay, so that the conductor did not move, but it was the needle which moved, because the needle was free to move. Remember this. So now the question is, okay, now the question is, we have seen the magnetic needle move. Now, can we make this conductor move? Okay, can we make the conductor move? Like I said, in this experiment, in OSS experiment, since the conductor was fixed, okay, we don't see the conductor moving. But if we change the experiment, if we perform the same experiment in a different setup, now our goal is, can we, instead of the needle, can we make this current carrying conductor move? What is my what is your answer, my dear students? What is your answer? I know my answer. Okay, so I know the answer, so I'm asking you, what is the answer? Can we make this current carrying conductor move? And the answer is yes, isn't it? We can make a carrying conductor move, and that's exactly what our lesson is. Look at the topic, my dear students. Force on a current carrying conductor. This current carrying conductor, okay, we are going to exert a force on a current carrying conductor. Who is going to exert a force on the current carrying conductor? This magnet. The magnet is about to take a revenge. So in Oyster experiment, it was the magnet who experienced a force. So revenge. This is a revenge. So now the magnet will take a revenge on the current carrying conductor. Okay, I'm just kidding. Okay, in science experiment there is no revenge. Okay, these are just experiments, and they don't do like that. They're not human beings that they will come and take revenge. No. Okay, so remember, we can make the current carrying conductor move, and this is what our lesson is. So like I said, I told you earlier that this backdrop, this quick revision, is only going to help you understand this experiment better. So in this experiment, we will see a current carrying conductor, okay, experiencing the force, experiencing the deflection. Whereas in OSS experiment, it was the magnetic needle, it was the magnetic substance, okay, which was experiencing the deflection. The reverse will happen in our topic today, which will be a current carrying conductor. That means the conductor where the current is moving will be the one to experience the deflection, to experience the force. So are we clear? So now, with your permission, can we confidently go and discuss this topic? Yes. Okay. So thank you for giving the permission. So now let's study in detail about our core topic, which is this. So now let us first do a thorough review, okay, of each and everything here. So let us first start with the stand. This is the stand, okay. This is the stand. This is the stand on which the whole experiment is set up. This is the base. This is the base on which this thing is erected. Now we have an extension, an extension, a metallic extension here to hang the current carrying conductor. This is the magnet. So let's go in detail. So first of all, we have the battery here. This is the source, okay. Remember, this is the source, and the source is always the battery, okay. Any experiment related with current, we need to have a source, and the source is always the battery. So the battery is a source. Now this is the positive terminal. So current will move out from this terminal. We have kept the key here, okay. Right now the switch is on. If I erase this, it is off. That means circuit is off. That means no current will flow, okay. Don't mind the current flow direction, okay, because we are going to start from this direction. So just ignore this for now. So this is off. If I want to make current flow, it will be drawn like this. This means key is inserted, okay. Off means key has been taken out. Since key has been taken out, it will be like this. So let's keep it off for now. So the wire goes here all the way, okay. Then it's curled here, okay. It's twisted and binded here, and then it goes down. And this is the current carrying conductor. This is the current carrying conductor, okay. Let's say this is A. Let's call this as A, and let's call this point to be B, okay. So this is A, this is B. I hope it's visible, okay. So this is B. Let's make it bigger, and let this is A, okay. And then the current carrying conductor is intentionally, I'm telling you, my dear students, intentionally, I can keep it like this, okay. This Andrew Mary Ampere, who did this experiment, okay, who did this setup, he could have kept it like this, okay, or he could have kept it like this, but then he intentionally kept it like this, inclined. There's a reason. So we will be discussing about this very soon also. So remember, this current carrying conductor is intentionally kept like this, okay, inclined, okay. It's intentionally kept like this. And then the wire touches here at point A, and then this is the conductor. So current will flow from one end of the conductor to the other end, and then point B is here. From here the wire goes up, okay, and the wire goes all to the negative terminal, okay. And then we have this horseshoe magnet. This is the horseshoe magnet. You know that this is called horseshoe magnet. And the north, okay, the north is downwards and the south is upwards, okay. So this is the setup. I've explained to you the setup. Now let us do some important things. So let me show you the magnetic field. Remember, magnetic field lines, they always move from north to south, okay. So the magnetic field lines here will be, let me just show you, this will be the magnetic field lines. The direction of the magnetic field lines from the magnet, it will be like this. It's always from north to south. So the magnetic field lines are from north to south. So they are going from here to the ceiling. My ceiling is up here. So from the floor, they're going up. Because the north pole is here, magnetic field lines, they emerge from the north and then they enter the south. So magnetic field lines are going upwards, 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 okay. I have just drawn 4, but there are many, okay. So now let's start the experiment. So positive terminals here. So let's insert the key. Key has been inserted, so current will flow. So current flow will take place. Let's say this is the current, so current flow will take place, and then current will first enter this point A. So right now current is entering from point A to point B. All right, so current first enters point A, then current will move to point B. So right now the direction of flow of current is from point A to point B. So current direction, okay, current direction of current, okay, is from A to B. At the beginning of the experiment, I'm following your textbook. I'm following exactly what is being mentioned in your textbook, because this is activity is there in the textbook. So I'm explaining accordingly, okay, as it is mentioned in the textbook. So at the beginning of the experiment, we take the current direction from A to B. So current is moving from point A first. Current first enters point A, then it moves to point B. So direction of current is from point A to point B. Now, remember this, my dear students, that we have already studied solenoid, okay, and from the solenoid, okay, it has been very clear, okay, I've told you very clear that the end from where the current enters is always considered as the south pole. So if this is a conductor, and if, okay, let's say this is the conductor, and if current plus minus plus minus plus minus, and if current, okay, and if current, okay, if positive terminal of the current flows from this end, from this, let's say x, and this is y, then the terminal on which the end point of the conductor on which the positive terminal of the battery connects is considered as the south pole, and the other one is considered as the north pole. Very, very, very important. Very, very important. I don't know how to do this. Let's do like this, or whatever we can do. Okay, whatever symbols you want to use. Just, I'm emphasizing that this is super important. Okay, super important. SIMP. Okay, super important. Simp. Okay, so super important. So very important. So remember the terminal. If the positive terminal of the battery is connected to this end, okay, which is your left, okay, so if it's connected to this end of the marker, then this end of the marker becomes the south pole. Very, very important. Okay, just insert it in your memory. It is very important. So the positive terminal, the end of the conductor where the positive terminal touches, is always considered to be the south pole. This is, we have already studied from the solenoid. Okay, so it's like a revision only. So now you tell me, my dear students, this is the current enters from this terminal, the positive terminal, okay, okay, touches NA. That means this will behave as south pole, yes or no? And then this is the other end of the conductor. The other end of the conductor will behave as north pole, okay, south pole, north pole. So this will behave as now north pole, yes or no? Yes, no? Okay. Now what will happen? And current now, let's continue with the current, and current goes from point B and all the way to the negative terminal. Okay, done. Now let's focus on these two poles which we have identified, south pole and north pole. So here, okay, here I have, so let me show you. So let's mark this. This is south pole, okay, so let me mark this. I have not marked anything here. So this is south pole, and ye ho gaya north pole. So south pole and north pole. Okay, now let me use this red marker. Now look here. Now from your orientation we will do, so this side is left, okay, so now let's keep it like this. So this is my left hand, and you're viewing from the angle you're viewing this video, this side is your left and this side becomes your right. So even me, let me orient it. So my left and your left is same, my right and your right is also same. So right now, okay, so remember black, let's say let this be north and let this white be south. Okay, so this is north, okay, and this is south. Okay, so north, if you orient properly, remember this red part is taken as north. Okay, remember this, the red part is the north and this white part is the south. So this is the right orientation, is it not? South is here, na? South. North is the red part, so north is here. So this is the right orientation of the conductor. Okay, and then see, north is here, south is here. So let's bring it here. Okay, let's bring it here in the clear region. So this is the orientation. Look here, north, north, south, south. South white part, north black or red part. So I'm just bringing it here. Now this is the orientation. Now you see, this is the south pole and this is the north pole. Now south and north pole, since the conductor is kept like this, now this pole, this north pole and south pole, they're very close. Look at check out the distance between here. They are very close, isn't it? They're very close. From north to north, the distance is quite far, but see, check out here. They're very close. South and north pole are very close. So south pole and north pole, two opposite poles are close to each other. So what will happen? Two magnetic, now this Now current is flowing through this conductor. Current is flowing through this conductor. Current is flowing through this conductor. So now this is not a normal conductor anymore, but this is a current carrying conductor. This conductor, since current flows through this conductor, now this is a current carrying conductor. And being a current carrying conductor, it will produce magnetic field lines, isn't it? Concentric magnetic field lines. Yes or no? Yes. So it produces magnetic field lines. So this current carrying conductor has now magnetic field lines. Okay. Now this is the south pole. This is the north pole. This is the south pole. So south pole, north pole. Now two opposite poles. So what type of interaction will it be? It will be a force of attraction. So the south pole will attract the north pole. So it will the current carrying conductor. Okay, the current carrying conductor will move towards the left. The current carrying conductor will be attracted. This is south pole and this is north pole. Remember, north pole, north pole. So south pole, north pole. Two opposite poles. What type of interaction we'll get? We get attraction. So the south pole attracts the north pole. So we have an attractive force. So this current carrying conductor will move towards the left. That's what is mentioned in your textbook also. It moves towards the left. I repeat, because this is south pole and this is north pole. This is north pole, this is south pole. Two opposite poles. The type of attraction, the interaction is a force of attraction. So the south pole attracts the north pole. So the current carrying conductor, okay, will move towards the left, which is what has been mentioned in your textbook. Okay, I hope it's clear. Okay, now, so when current moves from A to B, the deflection is, okay, the conductor moves left. It's not, the conductor moves left. Now what we will do is we will change the direction of current. So now we will make the current flow from direction of current will change. Let's make it move from B to A. So let's change it. That means we change this one. Okay. So I'll not erase anything, but now I'm telling you we will change the direction of current. Oh, well, let's change. Okay, plus, minus, everything has to change then. So this is long is plus, short minus, plus, minus, plus, minus. Okay, then this direction will also change. Now current will move from this position, from this direction. Current will move from this direction. This will also change like this. Then this will also change to like this. Then this will also change to like this. And finally it will go like this. And then it enters the negative terminal. So I hope it's clear. So now current flow, the direction of current flow has changed. Current will enter from this side. Current will travel from this side. Current is traveling all the way. And now it will enter point B first. So it will enter point B first. Okay, point B first. Then it will go to A. So the direction of current is from B to A. I repeat, the direction of current is from B. Current will first enter at point B. And current will move from B to A. From B to A it will move. And then it will go to the negative terminal. So direction of current from B to A. Okay. Then if we change the direction of current, will there be any change in the force? The answer is yes. So now let's go back to the same discussion. Previously, since current entered from this end A, this was considered south. Now you know what I'm about to do, isn't it? You're all smart enough. Yes, you're correct. You know what will happen. What's gonna happen now? Yes, current is entering from point B. The end from where current enters is considered to be which pole? Yes, very good. This is south pole. Ye ho gaya south. And this end will now behave as north pole. Now, you know what's gonna happen. The magnet has not been touched. The magnet is fixed in this experiment. Okay, till now we have not touched the magnet. So the magnet is still, the poles of the magnet are still there, north, down, south, up. Now, previously it was like this. Okay, south and north. Okay, this was north because current entered from this end. This was A and this was B. Current was entering from B earlier. Now current will enter from A. So now this red part will become south. Yes or no? This will become south. Now above it also south and this also south. So two south poles together. two south poles together. What type of magnetic field interaction we will experience? Correct. Now this time it is repulsion. It's not. Previously it was attraction. Now south pole and south pole. This is south pole, this is south pole. This part is south pole, this is south pole. So what type of interaction will it be? Two south pole, do they attract or repel? They repel. They repel each other. Jao, dur mujhse jao, na? Okay, so they repel. So they repel, so repulsion. So repulsion, because two like poles, they repel each other. So two south poles, this current carrying conductor will experience a force. This time it will be repulsion. Okay, so it will experience a force which is repulsion according to your textbook. Now let's orient it. So what is mentioned in your textbook? In your textbook it is mentioned it moves towards right side. Is it moving towards our right side? Yes, it's moving towards our right side. Okay, because it is experiencing a force of repulsion. Previously it was experiencing a force of attraction, so it was moving towards our left. Now it's moving towards our right. So it's moving towards our right because it is experiencing an opposite force. Okay, previously it was inside, now it is experiencing an opposite force because we have changed the direction of current. Now this is repulsive force. Repulsive force. Okay, so it's moving towards right. So it's moving towards right. So now conductor moves right. Okay, so what we have learned here is that when the direction of flow of current changes, okay, the magnetic field poles they reverse. So the magnetic field poles they reverse. So previously current was entering from B to A. When current enter from B to A, this is current direction. When current enter from B to A, this was south, this was north. But when we change the direction of current and when we made current enter from A to B, what happened? The magnetic field line, the pole of the magnetic field lines, they changed. So this became south and this became north. It's not, see? This is what happened, okay? So on changing the direction of current, the magnetic field, the poles of the magnetic field line, they change, okay? Remember this. This is very, very important. Now, now we have studied the direction that we have studied what happens when we change the direction of current. Now let us study, okay, what if we change the direction of the magnetic what if we change the poles of the magnet? What if we change the poles of the magnet? So let's do from here. Now, so currently right now we are here now. Right now the conductor is moving towards our right, because south and south are together, so the conductor is experiencing repulsion. Okay, now keeping the conductor fixed, okay, keeping the conductor as it is, and we don't change and not changing the direction of current now. So that means let the current enter from B to A, and now change the poles of the magnet. It was like this earlier. Remember, it was like this. Okay, it was like this. So now the north and south, we will exchange it. This will become north and this will become south. Then the magnetic field lines will change the direction. This will go down now. Because magnetic field lines, they move from north to the south. So now look here, this is south pole, this is north pole. Then what will happen? Now this is south, now it's like this. So previously south south, let me take back my marker. Okay, so previously south south, now suddenly this S, now see the direction. Okay, this south goes down and north comes up. So this white part is south, this also south. It was going like this. Now the magnetic poles have changed. Now north and south. So what will happen? Will it still go towards right side? No, no. Now it will go towards the left side. Why? Because this is north pole and this is south pole. Very true. You have understood. Okay, now it will go inwards. It will go towards your left. Got it? And then okay, and then now it's going towards our left. Then how do I change this? Okay, now what I will do is I'll change the direction of current. So let us make current. Okay, let us make current flow from A to B again. So now, if current flows from A to B, if we make current flow from A to B, then what will happen? What will happen? This will become south, and this will become north again. So north will be together. Then what will happen? It will go right again. So I hope you understood. Okay, if we change the direction of current, and if we change the direction of the magnetic poles also, if we change the direction of the poles also of the magnet, and if we change the direction of the current in the current getting conductor, the direction of deflection can be changed. That's what I want to tell you. So I hope this up till much things are clear. Okay, so if things are clear, then I'm most happy, because that is what I wanted to teach. So like I said, this is a very easy topic. Okay, this is an easy topic. It's not very difficult. All you have to do is understand slowly and gradually. Okay, and once you understand thoroughly what is happening, you will never forget. You will never forget. So try to understand the experiments. Okay, so of course we are not doing this, but then even reasoning also, you should be able to reason. All right. Now, so earlier I was telling you that Henry Mary Ampere intentionally kept the conductor like this. Now why so? There are reasons. So let's study. So there are three cases. Okay, case one. In case one, the conductor is kept like this. If the conductor is kept like this, inclined, okay, and this is the magnet. Now this is called incline. Okay, so incline, there's an angle here, certain angle is here. Okay, so incline. When the current carrying conductor is kept inclined, when the conductor is kept inclined, okay, case 2, will be when the conductor, okay, so the magnetic field lines are here, Case 2, when the conductor is kept perpendicular. Case 3, when the conductor is kept parallel. Okay, so when the conductor is kept inclined, and when the conductor is, see, when do you see there, conductor is perpendicular. Perpendicular to magnetic field, magnetic field lines. Okay, magnetic field lines. This is conductor inclined to magnetic field lines, and here conductor kept parallel to magnetic field lines. Now, here of these three cases, the maximum force, the maximum deflection, that means, okay, like this, maximum deflection, whether towards the right or towards the left, maximum deflection you will experience in case 2 here. So here you'll get maximum force. Remember this one, very important. When will the conductor experience maximum force? Towards the right or towards the left? It will be when the conductor is kept like this. When the conductor is kept like this, perpendicular to the magnetic field. When the angle is 90 degree. This is 90 degree. Remember this one, very important. Okay, so when the conductor is kept perpendicular to the magnetic field, we will experience maximum force. And when the conductor is kept at a certain angle, theta, okay, then here also we'll experience force. We'll experience a force, but not maximum. So a force will be experienced, but then this force will not be maximum. What about this one here? Here, no force. So remember this. In case 3, there is no force. When the conductor is kept parallel to the magnetic field lines, then no force. Okay, this conductor will not experience any force. So remember this 3. Okay, so I hope you have written this. Now we will erase this and then we'll discuss the next topic, which is the factors on which the force depends. So let us discuss the factors on which the force depends. Factors on which the force depends. Let's study this now. Factors on which the force depends. So the force which acts on the current carrying conductor depends on three factors. Let's study them one by one. So the first one is current. Now, what is the relationship between the force and the current? Remember this, my dear class, that force is directly proportional to current. What does it mean? It means this. So let's say this is the current, this is the magnet, and then we have the conductor in which current I is flowing. Then we have the same magnet and we have the same conductor in which current this time is 2I. So more current here, okay, so greater current here. Now, in which case A or case B, will the force experienced by the conductor be more? Correct, it will be in B. Okay, it will be in B. The force experienced by the conductor will be more in B because the force is directly proportional to current. That means more the current, more the force. That means if more current comes, then the force will be more. Okay. Then number 2, it is magnetic field. The second point is magnetic field. Now, what is the story of magnetic field with the force? The story of magnetic field with the force is directly proportional to the magnetic field again. So force is directly proportional to magnetic field. Now, what does it mean? It means this. So let's say this is the magnet and a current carrying conductor in which current I is flowing. Okay. Then let's take another magnet, but this time let's go for a bigger magnet because I want more magnetic field. So same conductor in which current I is flowing. Here the magnetic field is more, greater magnetic field. So if I ask you again, in which case A or case B, will the force be more? Then your answer should be, it will be more in case B. Okay, so greater force again because the magnetic field is more. Bringing a stronger magnet, this will produce more magnetic field. Okay, more magnetic field lines, thereby the deflection will be stronger. Now let's move to the third point, which is the third point is length of conductor inside magnetic field. Length of conductor inside magnetic field. Now, what does this mean? I don't understand what does it mean. That's what's going on in your mind. Okay, so let me tell you what it means. Length of conductor inside magnetic field means how much area of the conductor is under magnetic field. Still don't understand? Length of conductor inside magnetic field means how much area of the conductor is under magnetic field, which basically means, for example, let me show you an example. So let's say we have a short conductor like this, and we have a long conductor. Now, this conductor is short, so the magnetic field, the area under magnetic field will be less. So less magnetic field will produce, so the area under magnetic field will be less. This is wire A, and now this is a long conductor, so magnetic field, the area under magnetic field will be more here. As you can see, I am drawing many concentric circles. Each concentric circle represents the magnetic field. So you can see this is the conductor B. Conductor A, conductor B. Which conductor, A or B, has more area under magnetic field? Conductor B has got more area under magnetic field. That means this, okay, the force acting on this conductor will be more. Basically, if the current carrying conductor is short, for example, like this, okay, if the current carrying conductor, not curry, okay, not curry, but if the current carrying conductor is short, okay, the magnetic field line produced here will also be less, isn't it? But if we go for a longer conductor, then the magnetic field along the conductor will also be more. So basically, what will happen? The force experienced by the conductor will be tremendously high. Understood? So the force is also directly proportional to the length of the, okay, the force is directly proportional to the length of the conductor inside the magnetic field. That means this, okay, this will produce more magnetic field. So I hope that it is clear. Okay, so this will produce stronger force. Okay, so this conductor, because more area, okay, under magnetic field, this will produce stronger force. So I hope it's clear. So like I said, I hope I am able to keep my promise, which is that you have understood and you have mastered this topic, which is force on a current carrying conductor placed in a magnetic field. So thank you all, my dear students, for tuning in and watching. Now, goodbyes are always emotional, but then I don't want to say goodbye. So I'll not say goodbye, but then since the video will come to an end, I have a small homework for you. So I want you to practice this and comment the answer in the comment box. So the question for the day, I try to give a question at the end of every lecture, okay, so that we get to interact. So a current carrying conductor, so current is flowing here. Now this is, let's say this is south and this is north. So the current is flowing from south to north, and then a magnetic needle is kept here. Let me just indicate this. Okay, now this is the magnetic needle, this is the needle, magnetic needle, and this is a conductor in which current I is flowing. This is a current carrying conductor. The question is, in which direction will the needle deflect? Such an easy question. Okay, such an easy question. I should not be asking such an easy question. Okay, this is below your standard. Okay, but I want you to answer this question. So it will be up. Option A is up, option B is down, option C is right, or option D is left. So these are the options. I want you all to give me the correct answer. So will the needle deflect upwards or will it deflect downwards? Okay, well, I think these options are not possible, right and left, but just let it be. Okay, so I don't think the needle will go this or this side. So these two options are not eligible, but then, okay, just to create more competition. So will it be up or down? Such an easy question. So kindly comment the answer in the comment box. Okay, so that's it, my dear students. Thank you all very much from the bottom of my heart for tuning in, watching and learning. So this will be it, and I'll see you again in the next video. So until then, take good care and God bless you all.